Good morning, everyone. Today, excuse me, a little cold. Today is December 2019 and December 14th, I should say, 2019. And this is the John Chappell Natural Philosophy Society Science Chat. And I am your host, Franklin Hu. And if you would like to join us live, you can always go to live.naturalphilosophy.org and you can join in the discussion. We can have up to 6 people in the discussion at a time. And so if you'd like to speak and be part of the discussion, please join our live channel. Otherwise, you can go and hang out in either our Facebook or our YouTube site where you can just sit and watch. So, Bill, what's going on this week?
I discovered a couple hundred videos by a fellow named Robert Destini, and he has his own theory like many of us. But anyway, one thing I found was very interesting was he talked about what was wrong with the other theories in science. And I thought maybe one week we might do a video of what he had to say and then discuss that among ourselves that are online, because it would be kind of a third party talking about us, and we might discover some things about each of our own work that could be improved on or better defined or something like that. Not necessarily that he is always right or anything like that, but that it gives us a third party that's not particularly against what we have to say, but is being critical of science theories in general. And so what I would have to do is send that video to you so you could play it. And then
is that on YouTube or is it
it's
separate files?
I think it's on YouTube. If you go and look up Robert Destini, I guess.
Oh, I'm never going to be able to spell that. Can you put that in the chat?
Yeah, it's in there that I sent to you, I think. Can you see? I see it on the right-hand side where it says private chat.
Yeah, private chat. I'm not seeing any messages in the private chat yet.
Oh. I thought I sent it. Let me try it again.
I see it in the private chat.
Okay, maybe I'm not scrolled or something here.
It's the only thing in the private chat.
Okay,
yep,
now I've seen
sent it again. Yeah.
I don't know.
I don't know who this guy is, but he is very active on YouTube. You know, with I would say more than 100 half-hour to an hour videos, and so that might be an interesting way to use a third party that none of us know, I don't think, and see what they have to say. He has his own approach, just like many of us. So, but I think when I first heard this video, it did make quite an impression. So I went out and recorded all of his videos that I could find, and there's over 100 of them. So
okay, so we will be looking for something that's relatively short, maybe 10 minutes or so. Can you recommend one of these videos? Because there. Yeah, and this is www.distinti.com. That comes up when you put his name in there.
Uh-huh.
And he has 214 videos.
Yeah. So, well, I need to go through that list. I've been very busy since I did that work of copying them down. I'll try to send you the one I think I would recommend the best. He has only really one on that covers what is wrong with modern science theories. And so I think that one would be the one we want to do part of or whatever. And it's a presentation. It's kind of like a PowerPoint with his speaking, but he's also doing a certain amount of drawing and stuff like that on the screen.
Well,
Yeah.
I see one video here. It's only 4 minutes. It says "Kick It Up a Notch." This is where he claims that the reason why science has gotten nowhere with the, I guess, current mainstream thing here. So I don't know if that in particular is the video you would want to take a look at.
I'm trying to find out which one it was. It was.
Here he's mentioning about the Patreon site where, people can support you.
Yeah, his own theories involves the ideas about the ether and ether mechanics, and
I'm trying to understand what this particular video, because he's got like kind of fill in the blanks kind of thing.
Yeah, he has one that may be an introduction that's entitled. If I can find it. Etherian Mechanics Introduction, EM0100. But I'm not sure that's the one. I've seen so many. I have to go back and look at them again because but I was impressed with some of the arguments that he had about basically modern science that many of us are critical of too. And but his were different. A lot of his arguments are different than the ones that we're used to. So
now there is a video here from David. Actually, David DeHilster. He did a review on this website, I suppose.
Oh,
maybe that would be.
Maybe he'd be a good person to talk if he's available.
Let's see here. It says that David takes a look at his latest video and picks out some very important parts that show you this guy is truly someone you should listen to. Well, maybe we could listen to that for a little bit. That might seem like something that might be okay. Of course, I'm not quite sure whether the audio shows up when we actually share something. So we'll have to experiment around with that. So if I went and I did a share screen, and I went and I opened up a Chrome tab and I share the YouTube video. And if I start playing it, you guys tell me whether you can hear the audio or not.
I can see the video and the motion and everything, but I don't hear anything.
You don't hear anything? Okay, let's try this. Let's try it this way.
Another gem from a friend, as I say. This is from Lori Gardy, the Fractal Lady. She talks about fractals and how they work in.
Can you hear that?
Yes.
Yes.
Yeah. Okay. So why don't we just go ahead and watch a bit of this here, and you can interrupt at any time, I suppose, or I'll interrupt, or anyone can feel free to interrupt.
Hello, I'm David Hilscher. I am a critical thinker, dissident scientist. I'm here to tell you the truth about science. Some of the university professors won't tell you, the mass media won't tell you, and certainly those science experts won't tell you. This is another gem from a friend, as I say. This is from Lori Gardy, the Fractal Lady. She talks about fractals and how they work and maybe be a good model for black holes. Oh my gosh, that's pretty amazing, isn't it? But she pointed out somebody who I've never seen before or heard until just today, when I got an email from her and says, hey, found another critical thinker on the internet. His name is Robert Distinti, and he is an electrical engineer. How come all those electrical engineers are so feet on the ground, amazing scientists and real critical thinkers. I'm guessing it because they have to work with the real world, real circuits, real metals, real electricity, real fields, the whole thing. Because of that, they are amazing engineers and, in this case, great critical thinkers. So another electrical engineer, he started this this YouTube channel. Looks like in 2011. He's almost up to 200,000 views. He's even got a Patreon. He's got almost 2,000 subscribers. But I highly recommend you listen to this guy. He's just breaking down the rules of how you do science, and it is quite amazing. And that's what we're going to take a look at today. He does seem to be an etherist, I would guess, because he's talking about ethereal mechanics. That's his website, etherealmechanics.info. You can see it's pretty much just a bulletin board, but you can get in there and get your feet wet. But today I'm going to be listening to some parts of his discussion, his latest discussion. It's pretty new. I think it's within the last 24 hours. And he's redoing his, what he calls all of these ways that he looks at the world to rules of acquisition. He's looking at those rules of acquisition. And I tell you, this is really, really, I was totally fascinated to watch this whole thing. I can't wait to watch more of them. But I picked out certain areas that I thought were really interesting because it's on a theme that I'm going to be talking about a lot from now and in the future. Let's let him talk about it.
Cornerstone, I don't want to say supreme, other rules of acquisition. For example, rule of acquisition 11.2, irrefutability does not prove exclusivity. In other words, just because you have a theory that gives you right answers does not prove that there's not another theory out there that can't give you the same good answers. Because when I did my graduate thesis, and the dean of the School of Engineering said, "Well, what are you doing?" I said, "Well, I'm showing the models of electromagnetism." He goes, "Ridiculous. Maxwell's equations are irrefutable." Well, so what? That doesn't mean there's not another way. It's one of the differences between engineers and physicists. I don't understand what physicists are taught. They seem to be taught that there's only one right way. Engineers are taught over and over and over again there's more than one right way to solve a problem. Or maybe I should say it different. There's more than one way to solve a problem.
Is this blasphemy or what? The guy's talking about there are more than one way to solve a problem. Isn't this something I've been saying all along? That you can have the phenomenon like gravity and maybe have 5 models that describe it. We have ether models, we have particle models, we have lattice models, we have actually the distance models, and there are probably other ones out there, and all kinds of them. And you can't do that in science. He's right. Why is it that physics expects that we have this one thing, that when we find, I've talked about this many times, when we find what we call law, that all the people in the universe find it, all the intelligent beings are all going to find E = mc squared. They're all going to have the mathematical system that we have. They're all going to have the same models as we have. Because once we find the truth, it's truth forever. We can be like relativity, where Newton's so good to get close to speed of light. Now you have relativity, but you see, you're only building on it. You haven't thrown away Newton. You can't say Newton doesn't work as well, or you certainly can't have a totally different model from everybody else. What? But this guy goes on and talks and shows you these 3 loops. He goes out there on the internet and finds equations and finds different, theories or equations that all describe something in electrical engineering. He puts it to the test and describes it. It's pretty darn amazing. I'm not going to go through that because I want you to read it. Now I'm going to get to another part here, so bear with me. I got to get to 1428 here. We'll listen to some more.
To realize, because we may have a constrained footprint, there may be more than one model that fits this data. We have to go search for the other models, like I did for the field model. I did a computer search to find everything that would fit inductance data. When we do our search, we're going to have a polytheistic answer. Polytheism meaning more than one theory. And this is great. Now that we know that there's more than one theory to fit the data, what we have to do now is increase increasing our ability to sample more tightly so that we can disambiguate. In other words, take a sample here, and then if the dot comes here or the dot comes here, we would know which is the more truthful answer, and which is the less truthful answer. Okay? Rule of acquisition 1.1, because of our constrained footprint, we should expect and embrace polytheism. That means we have some empirical data. We should go find every possible way to explain that data, every theory, every mathematical model. Because once we find more than one that gives excellent results, well, then what we do is we go take more high detailed measurements to disambiguate which one it is. And therefore, instead of falling in love with the first one we got and printing like a little chicken, we're going to drive to the truth faster and faster. We're never going to get to the truth, but we're going to approach the truth faster and faster. Okay? And so, now we increased our footprint, our ability to measure. Now we can measure at a higher sample rate. And now we've disambiguated. But don't assume you're done, because nature can play a trick on you, and nature can still have another theory that's even that expanded footprint.
Boy, clicking all around, man, and getting all that wrong. He calls it polytheism. What does he call it? We'll go back here and take a look here. There it is. Polytheism. Polytheism. I had never heard that word before. That is absolutely fantastic. He gives this great example where you see, oh, this looks all good until you get here and he goes, oh, wait a minute, there could be something else going on there. Very true. Amazing, amazing, amazing. This guy is really putting something out there that tells us the same thing that I've been trying to tell everybody, and other people have been talking about this as well. We have different models. We all should work on them. We all should help each other, because one model is going to do something better than us. One example of that was during the Vancouver conference of the CNPS in 2017, beautiful Vancouver. My father was giving an interpretation using our model, the particle model, of why there are colors, different colors on a candle, because of the different movements of the nucleons of the atoms. And you know what happened? Duncan Shaw, who is an etherist and has what I call the Vancouver ether, this pretty neat model, very interesting model, says, hey, I can use that. Great. We're, like he says, like this guy's telling us, we get closer to the truth. No, we'll never get to the truth, ever. I mean, with the universe, we can't necessarily.
Did you say you're allowed to break in?
Workers, we certainly can't. We'll never. And this guy says the same thing. My father says very much the same thing. But the idea is that we should be. This should be normal in physics. It should be normal when you go to physics and you go to a university and want to be a physicist. It should be okay for you to come up with new models, and people will be debating those models to see which ones will work. Will the ether win out? Will the particle models win out? Will they be better than the other? We don't know. But if we don't try, we're not going to get anywhere. And like this guy says, our footprint, we're stuck. Our feet are stuck in the mud. This guy is worth watching. Go subscribe to him. I am going to try to get a hold of him, maybe even get an interview with this guy, because his stuff is fascinating. Please, please, please subscribe to him. Watch his stuff. He is a great critical thinker. He's got his own way of looking at the world and the way that we should be doing science. It is, boy, he is not easy. And I'm going to show you right here. I'm going to wrap this up and show you. He doesn't mince words when he criticizes.
Okay, beware of anybody who states that they have irrefutable knowledge about what anything is. If they say, well, I know exactly that this is that and that's that, I can tell you right now they're a complete moron. The best we can do is mimic what nature does. Knowing what something does is not knowledge of what it is. And that's the third rule of acquisition, which is the utility fallacy, which reads monkey do, does not mean monkey know.
I don't want to go and give you the whole thing. I can sit there and watch that. That's my problem. That's why you see me editing this, because I get so fascinated where things are, what things are doing, what this guy is saying. But This is a true critical thinker. Watch his stuff. I'm totally new. I've subscribed to his channel. I am absolutely on board with his polytheism. That is, let's use the models that we have. Ether models work very well with certain things. We have Jeff Yee with his really great ether model coming, and he's explaining that. Subscribe to his channel. We have the particle model. Subscribe to YouTube.particle.guru. We have a guy talking all about time and what that is. We need to look at all these things. That's Nick of Time. We have the Infinity Guru coming, because I just read his book, an amazing guy. Infinity is an amazing subject, and in my opinion, and this is mine because there aren't everybody. So some people believe it's infinity all the way down, but not up. I believe up and down. But infinity as a concept is really, really important for us to understand for all of our models. And so all of these things are there. And remember, don't take my word for it. Look at this stuff yourself. Subscribe to this guy. Don't take his word for it, my word for it, anybody's word for it. Look at it. Stay critical, stay thinking. I am Dave Beals, your science therapist. Ciao for now.
That's a very interesting video you got there, Franklin. And that gives you some of the ideas that I noticed in Robert Destini presentations. And the question that he raises is you don't really finish a theory because you may measure it more precisely in the future and see that your theory doesn't work. Like, for instance, general relativity theory was put forth to explain gravity, but then as we measured the gravitational field in Pioneer 10 and 11 in our solar system, and we measured it in spiral galaxies, we found something was missing. And so instead of falsifying general relativity theory, we invented dark matter and dark energy. And we keep going that way. Our scientific community, politically correct, is going that way. And that doesn't seem to be the best way. Maybe another approach could explain it, and you don't need dark matter and dark energy. But they don't want to be open to that. And so there's a lot going on. But being an experimentalist, he never closes or says, I finished my theory, now I go on to other theories, because he recognizes that you always can learn new things, and that may require another theory that can explain the same data but even more data.
Yeah, it's interesting that, his main thing seems to be about being open to different theories. And I was kind of impressed by, when David says that, people come up with their theories and they're kind of imprinted onto them like a little chick, and then they're just, stuck with them, and they kind of refuse to even consider some alternative theory. Rather than, I guess he's saying that you should embrace the other theories, and then by looking at both theories, trying to figure out some experiments where you can get a more fine-grained detail as to which one of these things is actually closer to the truth. So I think he's just not saying that all theories are good and all theories can be correct. Because I think he's still saying that eventually, since we think the world is one thing, that there will be one answer which is closest to the truth still, as opposed to just saying that all theories are valid and you're fine to stick with your own theory till death do you part, I suppose.
Yeah, we have different views in our group, I think, even on this topic. And my approach has been to say that we made a mistake in developing modern science, in that we changed our scientific method from the classical approach to what was called the existential approach, which means that we took the role of logic out of the scientific method. So if I have a scientific theory and it has an assumption in it that I later learn is false, logic says, oh, that theory can't be true. And so you should falsify the theory and find a better one. Well, we didn't do that.
Do we ever do that? Right?
No,
even as
we used to
dissidents,
do that.
we do that.
In the days of the ancient Greeks and in the times of Isaac Newton and people like that, we did that kind of thing, but we don't do it now. And now it's even more worse because we have in the postmodern philosophy of science, we have different silos for each area of science. And if the chemists, for instance, say, oh, we've shown that gravity is electromagnetic in origin, and the physicists don't like that, they say, oh, no, that's in your silo. Our silo has that gravity is not electromagnetic in origin, even though you prove it is. We don't like that idea. So
Now you're talking about between say us and the mainstream. I was kind of wondering. My point is that even us as dissidents, we're guilty of not taking into consideration either the arguments against our theories, or just simply continuing to not look at other people's theories. So this is what we do during the say the email things like this week. I was proposing that I say gravity is just an electrostatic effect, and one of the ways that could work is that it has to work on the dipoles that are in the material. So the dipoles have to align to the gravitational field, and so that one of the charges is closer than the other, and that is the general thing. So, but if you propose that, then one of the objections were that, well, then you would see a different gravitational forces depending on the type of substance that it was, because certainly some substances are more polarizable than others, and you might imagine that the more polarizable substances would, say, fall faster, I guess, due to increased force. And so we had to argue about those sorts of things. So it means clearly, that's one possible hypothesis. And one of the possible predictions that you might say is that the force of gravity might be determined by polarizability, I suppose. But now, as a person trying to defend that particular theory, am I trying to ignore that, or am I trying to accept that? And in my responses, I had to say that, and maybe some of my views are changed now a little bit, because and I responded by saying that, yeah, if you measured it carefully, then probably you would see a small difference between certain different materials, but you'd have to look specifically for polarizability, I suppose. That's not something that people generally look for. I mean, in these experiments where they determine that everything falls at the same rate, they'll take a block of wood, they'll take iron bolt, any different kind of material, but not specifically look at something that might be, say, highly polarizable. Say, compare water against, which is highly polarizable, against, say, ceramic, where we think everything is locked in place. Things like that, I suppose. But at least I think I'm trying to be more open to that possibility.
Yeah. Well,
Getting
I guess
back
yours.
to-
go ahead.
if I may jump in, getting back to Destini's dynasty.com and that presentation, which was very, very interesting. It seems to me that that presentation made me focus on how we rank different possible theories concerning how we rank them as to which one is best in this idea of polytheism. that the different theories are not equal, in fact. For example, which theories give the most predictions? Which, in the curves where he showed two sine waves, one of higher frequency and one of lower frequency in that illustration, where all the dots measured points fell on both of the two frequencies, one can calculate what the odds are by chance that those measurements would fall on the two different frequencies. And I would dare say the odds of one frequency being the one that would have much lower odds to get points actually on the sine wave curve that he showed. And so actually he was sort of claiming that maybe the lower frequency and the higher frequencies are sort of co-equal in terms of their explaining the measurements. I think that's in fact not correct. I'm not saying that polytheism is to be thrown out the window as an idea, but in the specific example he gave, he left out the ability to calculate the sort of the expected coincidence between the measured points and a particular frequency, and define one is very high and one's very low. And so where the coincidence is very high, that votes for that frequency being the one that is actually underlying the phenomena. Another way to rank theories in this so-called polytheism idea is the amount of data to be explained. For example, in Dr. Lucas's presentation, he has claimed, and I have no reason to question his claims, as a matter of fact, I'm very interested in them, that his work explains more data than other theories. And so that would rank his work higher than those other theories in that sort of a case. So the amount of data explained is a very important variable. Another variable, I just made a little list here while you other folks were talking. It's not a complete list, but the last item on my little list so far is the degree of parsimony in the theory as a way to rank which theory is better than the other. And so to summarize the number of predictions made, like string theory is notorious for making very few predictions, right? And at least so they say. What is the best fit of the data with which theory or the other theory? That's the calculated probabilities I was mentioning. And the amount of data explained as the third item. And lastly, to close, the degree of parsimony in the theory. And, you know, it's sort of like the ratio of axioms or postulated things to the amount of information explained by those axioms and postulated things. End of story, end of speech. But I find today's topic very interesting.
Well, another thing I would like to mention is I've been studying the theory of the nucleus and the atom, of course, and in developing the theory of the nucleus, at one point we invented the strong interaction force to hold the protons together in the nucleus, and the weak interaction force to govern the decay of nuclear isotopes. And then NIST introduced a program to measure the mass of all the observed nuclear isotopes that we can measure, which turns out to be about 3,500. And when you do that, and they measured it to 8 significant figures, before they'd only measured it to 3 or 4, it turns out that if you make a graph of the mass of all of the nuclear isotopes with the same total number of neutrons and protons, that the graph shows that the force that's holding it together is a 1 over r squared force. But these theories of strong interaction, weak interaction go as 1 over r cubed and 1 over r to the 5th. And there's no evidence for that anymore in there. But what was the approach? that we're taking in science. Oh, forget about that data. It must be something wrong with it. We must be analyzing it the wrong way. We know that the strong interaction and the weak interaction exists in the atom, in the nucleus. And so what is the best approach? It seems like the best approach should be the one that explains the most data. And also you have to leave the door open, because look at the history of the theory of the atom. I mean, first of all, it was indivisible. Now we broke it down into protons, electrons, and neutrons, and then we had to add strong interaction force and weak interaction force, and all these things over time. Well, what prevents something new from happening? Something new that we're going to measure, and how do we deal with that? What we're doing with our theories right now, the politically correct ones, is we ignore the data that doesn't agree with our theory. But this fella, Robert Distinti, he's an engineer. Engineers want it to work. You know, they don't ignore some of the data. They keep the data in mind, because when you're building an apparatus or something, you want it to work for what your goal was. And if you ignore some of the data, well, that'll cause your thing not to work. And so I think he thinks that we ought to always be open for new theories and not to discard them just because they can explain a few more pieces of data than we could in the past. And
yeah, I always kind of felt that, you know, the strong force falls in kind of the same category as, say, dark energy and dark matter, in that it's not anything we actually know how it works, but it was just sort of invented to kind of fill in the blanks. because you know, as soon as they came up with the idea that all the protons are concentrated in one place, they had to explain away why they don't all fly apart. And
yeah.
lo and behold, they come up with something called the strong force, a force which is the strongest force in the universe at the nucleus level, but is zero everywhere else, right? And it's like it's such an absurd force to consider. Or otherwise, you know, you'd have. I mean, both of us say our atomic models, you know, get rid of the strong force and just replace it with, say, the electrostatic force. Atoms being held together by just the Coulomb force. But I was kind of wondering, does Robert have any ideas on atomic level physics like we do? Did you see any? Because ether physics is one thing that kind of just explains how space is structured. But did you find anything about his ideas about atomic theory, like, you know, how helium is formed, or, you know, what a uranium atom looks like, or anything like that?
He has quite a few presentations, and he goes through, you know, Newton's laws and the idea of inertial mass and gravitational mass and many different types of questions. And he tries to show that we're avoiding things that the experimentalists think you should take into account. And so that's what he's trying to emphasize. And he has an idea of the ether and trying to explain a lot of these things in terms of the ether. But and many of us have similar type of ideas, so they have a lot in common. And so I guess the question is, he tries to say we shouldn't be so dogmatic that there's only one theory that works for this data that you're measuring, because what we see historically is we're always finding new data. And the new data, we have to invent a new theory for. Well, you know what I mean. When we started with the atom, we didn't need strong interaction, weak interaction. We didn't need neutrons in the nucleus, but then over time we did, and so we added that sort of thing. And
Well, one thing I wanted to ask you about, Dr. Lucas, is what is your opinion on the role of the neutron, or what do you think it really is? Now, I know that you have stated that, for example, the neutron doesn't exist, and I would agree maybe it doesn't exist as a separate particle, but why do you think the neutron has to be present in the quantities that are seen? Because it's like, given, say, a lithium atom, there are only so many neutrons you can add to a lithium atom. Why can we not add like 39 neutrons to a lithium atom? Or why can't we have have 0 neutrons in a lithium atom? They've measured these things quite carefully about what all the possible isotopes are, and there's definitely, they have a band, they have the chart showing what the limitations are. So why do you think neutrons have? Well, what are neutrons? What do you think they really are, if they're not really particles? And what do you think is their role?
Well, the having been an experimentalist like this brother Robert Destini, we made beams of neutrons. So we think, the experimentalists think, that neutrons exist as an elementary particle. But that doesn't necessarily mean that they occur in a nucleus. And so we have over 100 elementary particles that we've been able to make and to make a beam of and do experiments with. The various theories say they're up to 500 elementary particles, but we can't make beams of most of them, and we can't perform experiments with them, but our theories require it. So that's why we think they exist. And but in the case of the say the nucleus, it turns out that whatever is going on inside the nucleus, you can show it has a 1/r² force only present in the nucleus. And that was what the NIST data showed. And since it was done on 3,500 nuclear isotopes, the 8 significant figures, I mean, it's much more detailed than just talking about 90 some different types of atoms. You're talking about a lot of nuclear data. And so the way that I worked on explaining that was the force that holds the protons together in the nucleus is that you have shells of protons, and then an alternating shell of electrons, and then another shell of protons, and they get real close together. And when they're close together, the magnetic force is stronger than the Coulomb repulsion, and so that's what holds it together. And you can kind of think of that if you look at the different shells. The shells can be alternating plus and minus charge in the various shells inside the nucleus, and then of course outside the nucleus in the electron shells, they're not alternating proton and electron. They're much further apart, and they're just electron shells. So there are ways to see that, and that appears to be the best way that we know of so far. But someone may discover some more data or measure something more precisely than we've done before, and the theory is that we might take the approaches may be incomplete. And so that, I think, is what Robert Destini is trying to say. And I think he's trying to say we need to be open to multiple approaches. Just because we have one approach that may seem to explain all the data we observe now, it doesn't mean we're not going to observe some more data in the future that we didn't know about right now. And then what are we going to do? Well, what our politically correct scientists are doing is, oh, well, we don't want to falsify this theory. We like it. We like a lot of things about it, philosophical issues about it and all that kind of stuff. And so what we're going to do is we're going to invent another theory to supplement the first theory so that we don't have to falsify it.
Well, maybe this is a good example, say, because our atomic models would be an example of polytheism, how the atoms would form. So you were saying that within, say, the core of the atom, you have alternating level layers of protons and electrons and protons. But at some point, you just have electrons. Is that correct?
Yeah, you have more electrons. Well, you have to have the same number of electrons as protons in order to have a stable atom.
Yeah, so apparently the concentration of protons is, say, much higher than the surrounding electron shell, such that there's a surplus of protons still to support the outer electron shells.
That's right.
So,
No.
Okay, just trying to understand your theory here. So that's one possible theory of how the atom is structured. So that would be, say, in opposition to, say, my own theory of atomic structure, which says that actually the protons and electrons are all exactly paired with each other. So as you grow out the atom, it's all completely just dipoles, really. And it expands out. So the major difference would be here is that there wouldn't be any regions where you would have to have just electrons only. So wherever you had a proton, you would have to have an electron right next to it. So that's another possible example there. So, but the question is, according to, say, Robert, is how would we distinguish between answer to the truth?
So, Bill, can I ask you a question?
Sure.
About your model here? Would you then agree with, for example, I can't remember the guy's name, but the company name, Brilliant Light Power, used to be Black Light Power, in which the quantum mechanics ground state in standard textbooks is not the ground state, and that the electron, for example, in the hydrogen atom, can go closer to the nucleus, the proton, and so the ground state of quantum mechanics is not the ground state. The electron can get much closer to the proton, particularly in the nucleus. According to your model, it sounds like you would also agree that the ground state that we call in quantum mechanics is not the ground state. It can actually, the electron can go to much lower energy states.
Well, I should comment a little bit here. I had a son who went to Science and Tech High School, and he wanted a 4-year science project, and I got him to work on a new theory of the atom. And that theory of the atom, it was based on the experimental work of Arthur Compton and Winston Bostick, where they found that the building block of all elementary particles appears to be the soliton of the electromagnetic field. And soliton is a very strong standing wave, stronger than anything else we have ever found. And so when we did a theory of the atom, this soliton was in the shape of a toroidal ring. So that in order to have quantum effects in the atom, the electron did not orbit the nucleus. The electron was at equilibrium at a certain distance from the nucleus, and the quantum effects were the wavelengths that could be supported within the toroidal ring. So you could have a wavelength that was 1 circumference of the ring, or 2 circumferences of the ring, or 3, and that is sort of equivalent to the older theories of the atom. But you could also have a wavelength that was 2 wavelengths in the ring. shorter wavelength, much higher energy. And NASA measured the emission spectra of hydrogen atoms in space, and where they didn't have to hold it in a glass container and excite it and get the light to come out and then run it through a grating. And they just let it come through an opening in the rocket. They put the rocket up on the dark side of the Earth and away from the sun, and they had it pointed toward the darkest place they could see away from the Earth. And they opened the window, so it wasn't a piece of glass there or anything, and they let the light come in onto a grating, and then they looked at the spectrum that they got. And they got about 100 more lines. And since this was the darkest part of the Earth, darkest part of the universe, and the universe is 75% hydrogen, they figured that was mostly from hydrogen and a little bit from helium. And so they looked at these spectral lines and they said, oh, these spectrum lines in the extreme ultraviolet cannot be explained by any of our quantum theories of the atom, where you have a particle orbiting the atom, and it's the orbit that produces the wavelength, the quantized value. But in the terms of a toroidal ring, you can have standing waves of different wavelengths in the toroidal ring, and one of those types of standing waves is 2 wavelengths in one circumference and 3 wavelengths, etc. So they looked at this, and they found that, my son looked at this, and he found that he could predict precisely every single line they observed in the energy range in the extreme ultraviolet, and no more. And he got them all right within their experimental error. And so,
is there a paper on the net on that?
oh yes, and it won the grand prize at the International Science Fair for high school students. That's the worldwide science fair, as a new theory.
So there's like a URL where we can go and read that paper.
Yeah, it's on the Common Sense Science. Common Sense Science.
I don't know if it's.
I didn't see any data on that on Common Science. I think I looked at every single page.
Common Sense Science only has what's in the journal. There are some articles that my son and I did together on that. If you are interested in that, I can send me an email and I'll send it to you. But
yeah, or if you can find it now and put it in the chat, that would be helpful. Although I'm not sure you're answering Bob's question, which was specifically about the ground state of an electron. I think your main point was that the electron does not orbit the proton.
But its ground state is one wavelength around the circumference of the toroidal ring.
Right. And so Randall Mills theory, that's the guy's name, Randall Mills theory, says, for example, that the principal quantum number n, which can only be integers and can be no less than 1, is not correct.
That's right.
That you can have n equal a half, a third, and that's what Bill is saying. Well, it doesn't have to be just once around the torus. It can be 2 times around the torus, which is a half, or 3 times around the torus.
No, the 2 times around the torus is 2.
Okay.
So the regular quantum numbers 1, 2, 3, 4 are the number of times it goes around the toroidal ring to complete the standing wave. And so in other words, the standing wave, has a up and down a couple of times, and in terms of the amplitude. And my son did an experiment. We wrote a letter to the people that make the what do you call these springs that can jump and hop down the steps and stuff like that.
Slinkies,
yeah. We wrote a letter to them and told them about the experiment we were doing, and they sent us a slinky that was continuous. In other words, it was fastened so that it's just one toroidal ring. And then we hung it cord with string. So we had a lot of strings holding it in a toroidal ring, and then we took a metronome, and which had a little hammer on it, and we made it hit the ring at different frequencies, and so we could find what standing waves were there, and so we could actually observe various standing waves of different frequencies, different wavelengths in this toroidal ring of a particular geometrical size. And so that was how we were able to demonstrate what the standing waves would be in the toroidal ring, because we didn't know for sure whether a toroidal ring could support wavelengths of n equal 1/2, 2, 3, 4, 1/3, all those things. We just assumed they could until we did the experiment, and then we found, yeah, you could do that. So we have now a physical origin of quantum effects instead of a separate theory called quantum mechanics. And so that we eliminated quantum mechanics as a separate theory, so that everything was physically determined in a more classical approach. And
now, is the n that you're talking about, like you say, the integer numbers, those are the ones we use in say determining the spectra? The n is like 1/n squared minus 1/n squared.
Right.
Where the n's are, where theoretically the Bohr orbit levels. Is that what?
Yeah. That,
because I don't know how that relates to what you're talking about with the standing wave. See, that's just a complete disconnect for me.
That n is telling you how much bigger the orbits would be for electrons in an atom. In other words, the n equal 1 is the lowest, closest electron to the nucleus. And then when you get up to n equal 2, and 3 and 4, you're getting bigger. And then when you have a transition from one of those levels, say n equal 2 to n equal 1, you have a certain amount of energy given off, and that's the emission spectral line. That's the current theory of the atom, like the Bohr model. But in the model we have, the electrons form shells, okay? But the individual electrons can be in an excited state, and they can have different standing waves in the toroidal ring. And so you don't have just one electron or one particular shell that produces a transition where an electron moves from one shell to another. You have the toroidal ring can be in an excited state. Any one of the electrons at any of the shells can do this.
Well, that would mean that the toroidal ring would have to be really big.
No.
Like, say, much bigger than the atom itself, right? Because they can get...
The toroidal ring remains the same size, no matter which standing wave state you're in. And that's what we proved with the slinky, hanging and using the metronome. We were able to make all of these different standing wave frequencies, and we could actually photograph them and see them. And
so you're saying the electron actually doesn't get further away?
No.
All you need is just one ring, same size. It's just ringing at different frequencies, is what you're saying, that when you put more, when you excite electrons by putting them, by ionizing them in a gas, that's how these spectral emission tubes work, right? And you're saying that the individual electron is staying at the same shape, but is somehow getting into a higher energy.
If you take into account the shape of the standing wave in the toroidal ring, in other words, there's an amplitude there, and so the field will show that amplitude. So if I look at the amplitude of the wave in the toroidal ring, I can see it. And it's a little more complex than what I'm saying, because in the the soliton of the electromagnetic field, there's two types of motion. There's a motion around the toroidal ring, the circumference, and there's a run around the cross section. And that's what we call the spin. And so when you've got spin orbit interactions that occur in a soliton or this toroidal ring, it's not a plane. It's not like a particle that's going in a circle. It's continuous and it's uncuttable. And so
actually, where is it? Because, let's just say the simplest example of, say, hydrogen. So you've got proton. I'll represent that by this red block. And then you've got the electron. Now, that electron has to be physically in space somewhere around the proton. I think maybe that's what Bob is asking about. In mainstream, they're saying that, you've got the spatial relationship is that the electron is orbiting, and that would be like n equals 1, and then you would have n equals 2, and you'd have n equals 3 with the electron getting in progressively larger orbits. But so what I'm understanding about your model is that, you have the electron, but it just simply has an N1 state. It's got, certain frequency going on, and N2 state, it's got, maybe faster frequency going on. And 3 state, it's, maybe going back at a higher frequency, but spatially, where is the electron?
And the electrons, there's a bunch of them up there. And if you make these toroidal rings like we did, we were able to show, what we did is we used ring magnets, and we were able to hang the ring magnets from a board and to produce the shell. In other words, what is the stable orientation and configuration of an electron shell, whether it has 2 or 8 or 18 or 32 or 50 electrons in it? What does it?
Well, that would be within an atom. So uranium has that many shells, but within a hydrogen atom, now obviously it doesn't build up those shells because there's actually only one electron, right? So I think that's important to kind of distinguish between the ends of the spectral lines, because
it turns out that you do make the shells, and that the hydrogen doesn't exist as a free atom. It usually is a molecule, which is, it's 2 hydrogens, 2 protons and 2 electrons. And so you've got that structure there, and that structure forms the shells that you can see. And we demonstrated that in our experiments that we did with this science fair project. It was
that would produce one shell. But we know from spectra that, you can have n equals 1, 2, 3, 4, 5, 6, 7, I don't know, like maybe 10.
Yeah.
I think what Franklin is referring to, if I'm not mistaken, is that when a hydrogen atom, or as Bill Lucas says, molecule, absorbs some energy, an electron would go, say, from shell 1 to shell 2.
No.
And then when it emits some energy back out, it goes back to the ground state where n is now 1. I think maybe Franklin is talking about this absorption process where the electron can be boosted up to shell 2 from shell 1 and so forth. Maybe.
Right.
I don't know.
But see,
Franklin.
like when we took the metronome and we were using it with this slinky that was hanging down, emulating our toroidal ring, our soliton. When we changed the frequency to be twice as high, then we'll get a different standing wave in the toroidal ring. The toroidal ring is, if you've seen a picture of the atom, you've got 2 let's look at helium. You've got 2 rings about the nucleus, and then inside the nucleus you've got rings also. But the rings are smaller because instead of all having the equivalent charge of an electron, they've got some with proton charges and some with electron charges. So they can get closer together, but they don't get all the way together because the magnetic force at short range is stronger than the Coulomb force. And so that's what keeps them apart. So when you have a transition that occurs in an atom, the transition is occurring in one soliton ring. You could have multiple rings doing it, but you would get multiple frequencies out of light. But if you just have one occurring, it can occur in any one of the shells, and it could be any one of the toroidal rings that changes its standing wave pattern. But the ring stays approximately the same size. It doesn't double in size or get half the size. It's the standing wave. Just so if I were plotting a wave that was in a circle, I could have a wavelength going around the circle once, or I could have the wavelength going around the circle twice, or I could have it going halfway around the circle. And so that's kind of what you see. So the reason that my son got the prize at the International Science Fair, and by the way, the judges at the International Science Fair were all Nobel Prize winners in physics. And none of them liked this because it disproved the work for which they had received a Nobel Prize. So
James, I was just kind of curious. So after hearing Bill's explanation, do you understand what he's talking about? Does that make sense? I'll admit I'm a bit confused.
Are you addressing me, Franklin?
Yes, I'm addressing you, James.
Hi. Okay. Well,
that's kind of
I would just say that one problem or issue I have, with all due respect to Dr. Lucas's explanations, is the lack of any indication as to what the smallest toroidal ring, or what he calls a soliton, what the smallest one of those is, its size. And it, here he's out predicting. I'm trying to sort of give you a little pep rally, Dr. Lucas. Here you're out doing some amazing things, predicting spectral lines and so forth. How come, in many weeks of hearing you talk about solphotons, I don't have any idea of what the radius is of a soliton, say the minimum one? I raise it because in my work I've quantized space, and I have a quantized length constant. It's about 2/3 of a femtometer. Mm-hmm. And in my work, the model of the electron, the individual charged quanta do circulate in a circle, which is much like the idea of a soliton. So,
but there's a difference.
I guess the question then is that I have, or the reaction, Franklin asked for a reaction, is I'm still waiting for, is there any theoretical basis? Maybe there's absolutely no theoretical basis in Dr. Lucas's work to tell us what the radius is of the soliton. The last time I raised this question, he said, well, the radius is not important, it's the circumference. But excuse me, sir, the radius is just another way to express the circumference. So that was sort of a non-answer, if I can respectfully say.
There's an answer to this question, and that is we are presenting an electrodynamic theory of the universe. So all fundamental constants have to be of electrodynamic origin. One of those constants is Heisenberg's constant for quantum mechanics. That is the ratio, is produced by the ratio of the thickness of the toroidal ring compared to the circumference or radius. I guess you say the cross-section radius to the other. And we're able to predict to the accuracy that the Heisenberg uncertainty or Heisenberg constant can be measured, we were able to predict that from pure theory, pure
But
electromagnetic.
still, you don't have a radius value.
Well,
You're predicting a ratio.
the radius depends on the environment. In other words, if I have one of these toroidal rings, and we've made them in the laboratory, and I put it on the end, I put a prong toward the center of it. Here, I don't know if you can see my hand here. Let's say this is a ring, and I put a prong going like this. The ring will stick to the prong. I can now put that prong in all different kinds of environment, and it will change size. Okay.
So there's no such thing. Maybe what I'm doing is, with all due respect to the many great achievements of Dr. Lucas, maybe I'm adding a little excitement to our Saturday chats. I don't know, a little give and take here. I mean, so in other words, whenever I raise the question of what the size is, the answer is it could be anything.
Yeah. What the size is in the politically,
which leads me to believe that there's a big hole in your thinking.
Well,
or I'm completely wrong about quantizing space-time and energy. It's got to be sort of one or the other.
Suppose there was a number. It's kind of like the question I was trying to drive at is like, mechanically, are you buying this idea that there's standing waves and the whole toroidal ring thing?
Well, this toroidal ring thing is based on experiment of Winston Bostick and Arthur Compton. So
yes, but Robert has said that that's good, that might be useful, but doesn't necessarily say that that's necessarily the right thing.
But now, the size of the ring is not a fixed thing like we would think of as a hard particle, like a marble or something. It's the toroidal ring, which is a soliton, is affected by local fields. And so if I take a soliton and I bring it up to let's say it's a nucleus with no other electrons around, no other electrons outside the nucleus. If I bring it up, it's a certain size. As I get closer to the nucleus, it's going to shrink. And if I put it inside the nucleus, it's going to be even smaller.
Well, we'll see, Dr. Franklin. At least I have a little bit of common ground with Franklin in that he agrees that somehow space is quantized into cubic areas where objects can then exist in those cubes and so forth. But what you're so I might push it to the limit and say, are you saying a soliton could even be smaller than the Planck length, which is what, 10 to the minus 33 meters, or what's the number there? Are you saying it could be even smaller than that? In other words, there's actually no limit to what the soliton size could be?
We in doing scattering experiments, we can see the size of the particles inside nuclei. And we can see the size of an individual particle like a proton. And we can also see the size of an electron that's outside of atoms.
Yes, I know. That's how I found the fundamental, what I'm calling the fundamental length constant, from scattering data of protons, indicating their size was somewhere around 1.3 femtometers.
You should be able to.
But you apparently in your work, I just want to make it clear, it's not good or bad, sir. It's just for me to know and for others to know. I mean, apparently your work does not shed any light as to what any kind of fixed size that a soliton would have. You're just sort of saying it could be anything.
It doesn't have a fixed size.
Well, that would indicate to me that everything in physics has a fixed size except this.
No.
So, I mean, this is sort of like beyond physics. I mean, I'm almost speechless, so let me be quiet.
Hans Poincaré, who developed the theory for natural philosophy, natural science, he did a number of theorems in meta theory, and he said that the electromagnetic force and the gravitational force have to be, how do you put it, the same on all size scales. The structure, I guess you'd say, is the same on all size scales. So what happens is if we look out into
And all be below the Planck's constant? When you say all size scales, it means it could be 1/1000th the size of the Planck constant for
the
length.
Planck constant has never
The
been
Planck length, I should have said. Excuse me,
Yeah.
correction. I should
yeah,
have said
it
the
has
Planck
never
length.
been observed. It's a feature of a particular theories. Okay, it's I don't know how else to say it, but we don't need to talk about the Planck length to explain the observable phenomena that we've seen so far. We have theories that use it, but we don't need that because we have other theories that don't need it and explain the same thing and even better.
Okay, so if that logic is acceptable and it might make sense, it might hold water, it still doesn't mean that the question does not exist as to what the size or minimal size of a soliton is.
Well,
And when you
could-
say it could be anything, at least if you say, well, it's greater than the Planck length, at least you're giving it a range of size. I mean,
Winston
the
Bostic,
Planck length is greater,
let me
but
tell you some experiments that were done. Winston
you
Bostic
don't even want to do that.
ring this big around, about 6 inches in diameter. He mounted it on a metal prong, put it in a jet airplane, used something like a microwave heater and put energy into it, millions of degrees, and flew the jet plane around the Earth. And the observers there were from NASA, commercial airlines, and the military. And they all observed that this plane flying on one soliton could go faster than any other plane or rocket they had ever made.
Although that soliton may or may not have anything to do with atomic physics. I mean, if that is indeed true, that is certainly an
No,
interesting
the soliton
thing.
was this big, but most solitons are much smaller than that. But they come in all different sizes.
Yeah, I think
But
one
the
way
shell that it's in determines.
Although I'm not quite sure what the obsession with size is myself.
Yeah.
I don't really have any big objection with that.
I'm just a little skeptical. Forget my work on space-time energy quantization. Anything in physics where the size is sort of irrelevant. I mean,
well, things can certainly be scalable.
Certainly, everything in astronomy and physics, people are very much concerned on what is the diameter of the Earth, what is the size of the Moon, what is its density.
I think you're talking.
And what you're
past
saying
each other.
There's an object that has no particular size.
No. Hang on. I think, first of all, I put in the chat a link to Bill's paper, which has some of the information on that background UV measurements.
I copied
other
that
issue,
and I'm going to look it up.
The other issue on the size of these things, at any one time, I think Bill is saying, yes, it does have a size. But if you take this soliton or toroidal ring and put it in a different environment, for example, if it's originally not in a magnetic field, external magnetic field, and you bring it into an external magnetic field, the size has to adjust because of the inductance. It has to, I think, keep the same magnetic flux through it or something. So it would have to change the quote-unquote current making up that ring, and the way it does that is by adjusting its overall size. So the size of the solenoid or torus ring is always has a certain size, but in whatever environment you go into, it has to adjust to the local fields that it is being put into.
Yeah, that's right.
Okay. Well, okay. I mean, that can sound like clear thinking, but I want to remind the listener and the group here that all of this work is based upon the continuous space-time theory. which I believe is an era which is ending in physics, by the way, that we're going into a quantized space-time theory that's going to be most productive, most predictive, et cetera, et cetera. So with that caveat, well, what I would be interested in, let's put it this way. I mean, it may be irrelevant to Dr. Lucas's work and other people's work. I can accept that. But for me, it is very relevant. What is the smallest soliton size possible? And my theory predicts what that is. Look at the model of the electron in my work, that the diameter.
Of course, there's always a possibility that the soliton just simply doesn't exist, and it's only exists on blackboards. In which case, you can't predict what the smallest size of something which is completely imaginary. It would be another problem.
But
It's
Well, it exists with continuous space-time theory, which is Maxwell's equations and all the equations that Dr. Lucas uses, which is based upon continuous space-time theory. It exists. In quantized space theory, it exists in the model in its smallest size of the model of the electron. Now, when we say there could be larger ones, sure, there could be orbits or pathways that quanta related to electrons flow and make larger solitons. My work allows that. But my work does demand, and maybe no one else demands it, but my work demands that there's a minimal size of the soliton. If there's not, my work's completely out the window.
Well, maybe not necessarily a soliton, but that there is a minimum measurable distance of something, right? Since me personally, I don't think solitons exist, really. I think that's something that's wrong with Dr. Lucas's theory. In all due respect, I think it's just completely wrong, can't be justified, and that, of course, would just be my opinion. But it's up to me as an alternative theorist to explain the same things that he does, right?
Because I think Dr. Lucas's work, not to talk over you, sorry, but actually is confirming and entirely consistent with my work, and it would be consistent if someone could show that the smallest soliton possible is the one where the negatively charged M bit is circling in the radius specified by the binary mechanics primary length constant in what I'm calling the spatial object called the electron spot. If someone can show me that a soliton, a measurable experiment or whatever, where a soliton could be smaller than that, it totally wipes out binary mechanics. I throw it in the trash can, set all the papers on fire, and go out in my garden and work on my coffee tree.
Don't go that far.
No, I think Robert would say that you need to go and just consider if there's some problem with your theory, that you need to go consider the other theories and not be so imprinted on your own original theory. Right? That's what.
I'll work on the coffee trees and the day to do the weeding and so forth, because the vines tend to grow over them and kill them if I don't. But then at night, other times, I look at other possibilities in physics. Sure.
I think that's what Robert was trying to point us out to, is that if it is found out, well, first of all, that we should be open to the possibility that our theory is wrong, and we have to be willing to take all our theories, throw them in the trash pile and light them on fire. But the thing is that if we do that, we shouldn't just give up and retire and grow coffee beans. That we should still continue to look at the Pauli theories and find out which one is more plausible.
True. I agree with Franklin 100% here. That's why I'm here. I want to hear what other people think.
So, James? That's one possibility. We've kind of been exploring.
I already know what I think. I want to hear what you all think, about everything.
So I'm saying that Bill is wrong.
I want to learn about it. I want to know about
Bill is not right here. So,
James,
I think his obsession with toroids is throwing him off, I think.
Well, so, James, I wanted to ask you about your binary theory a little bit. I'm trying to read it Having a little difficulty with it.
Thank you.
But I'll keep trying. I'm wondering how, or if you have a paper on or some website or some info on how you go from such a, how do I say it, a low scale and build up to, have you been able to build up to what we would call, for example, classical electrodynamics differential equations or an integral form, something that could either assist in showing why Maxwell's equations are correct, or showing that no, Maxwell's equation isn't quite correct and here's what you need to change, or some correction. I want to say from the binary level to almost like an engineering level. Have you been able to bridge that gap?
Okay, well, in my work, sir, the basic thing is you have a definition of a system state, which I call the bit function, and then the time development of that system state, which are bit operations, of which there are 4. Now, I divide, there's an electrostatic bit operation, and there is a magnetic, or what I call the vector bit operation. And that those two are separate, and they're ordered. The results in terms of how the system state develops and changes depends upon the order of those. I think I found the correct order, which is diametrically opposed to, say, the Lorentz force equation, which I think is related, of course, to Maxwell's work, where you have the magnetic and electric components, the A vector, you know, and the E field in the Lorentz force equation are said to operate simultaneously. So I would expect that this false assertion, in my opinion, that these two act simultaneously will show up in some anomalies in people's work, and that's one reason I'm here. If you got any anomalies, I'd love to know them. You know, which would verify my work, showing that there is a definite order of the 4-bit operations, which are the momentum-related one, which I call the unconditional bit operation, the electrostatic one, which I call the scalar bit operation, just you know, because years ago I was reading books by Feynman, okay, in physics, and he called them the vector and the scalar operations, okay. It's just a label. And so then you have the last one being the strong bit operation, which is left out of Lucas's work. Okay. The strong bit operation was discovered by the fact that bits applying the basic axioms that you can read in binary mechanics, that bits will tend to cycle in one of 2 bit cycles, the proton and the electron. And those cycles will tend to capture incoming quanta. When I say bits, in this case, I'm saying 1-state bits. So I'll end the speech there. But any problems you have in absorbing binary mechanics, I would love to know what they are and address those specifically, because in a way, binary mechanics is extremely simple. It's ironic that I've used the classical laws, such as the Coulomb law, to derive the electric charge in binary mechanics from first principles. And as far as I know, I'm the only one to derive that without other observed constants on the other side of the equation, just the primary first principles. So that's where some of your math, like as far as where are the differential equations and what is their role. It turns out that the Dirac-Spinner equation, the spinners really give you a list of 8 differential equations, okay, with 2 pairs of opposite-handedness Dirac equations, which is, by the way, how the positron was postulated and discovered finally, okay? I use that exact 2 pairs of Dirac-Spinner relativistic spinner equations divided into the two pairs being of opposite handedness. You get the 8 differential equations. A genius named James Hughes, I want to give him credit. That's Hughes, James Hughes. He was a former MIT student in the 1970s. He showed that by simple matrix operations, you can rotate these spinors in the pair of Dirac equations. That's the 8 differential equations. You'd have 4 if you just had one of them. But if you have 2, a pair, you've got 8. And show that they really correspond. They are synonymous with the points of a cube. So what Hughes, in a way, discovered is that while everyone had thought that these quantum mechanical equations, such as those of Schrödinger, as well, and particularly of Dirac with the spinors in there, actually refer to events not at one point, but at 8 different points. And that was my starting point to get the 8 points of the spot cube and the model of space, and to say, so when Hughes did that, he actually wanted, this was years after he actually did this. Originally, he was over in my kitchen where I had a blackboard on the wall in the kitchen to deal with math equations and things like that. He wanted to present his work to me to see if I could find anything wrong with it, because I just happen to be pretty quick when it comes to math things. And so I couldn't find any problem with it. And then I said, well, son of a gun, let's just take everything that Hughes did, because that's where he left off, in my opinion, and quantize everything, space, time, energy, the whole shebang, and see where it gets us. End of speech.
So I see we have Toby here, and he was asking the question here, do you
Toby,
accept the radius diameter of the electron as given by the standard physics models? So my comment on that is that according to classical, mainstream physics, they've not been able to measure or find a radius for the electron. It's as close to a point particle as they can experimentally measure. Although there is this thing called the classical electron radius, which is kind of a made-up number, but it's still, I don't know, I guess useful, but shouldn't actually be considered an actual radius for the electron. That is at least my understanding.
In my work is about 0.8 femtometers, and so that would be the radius of Dr. Lucas's smallest soliton, to be consistent with my work. Again, if it could be demonstrated that there was a smaller one than that, it would completely, pretty much, throw out or falsify the work I've done thus far in quantizing space-time and energy. So that you see, if you look at my derivations of the basic constants like Planck's constant, the electron magnetic moment, which should be a real winner in Dr. Lucas's room there, and others, the speed of light and so forth. Almost all are based upon traditional classical notions. Like, for example, I use the classic equation for dipole magnetic moment, the classic one, the current around an area. Okay, that's your pre-quantum mechanics physics books have that, and to derive the electron magnetic moment. So that in answer to the question, what about some of these differential equations and other equations in physics, I've used them. They give the classical equations, which is similar to, in spirit, to Dr. Lucas's work, which is why I have so much interest in his work, have been used to derive all of the fundamental constants, which is the basic, the greatest body of unobserved data, of unexplained data, I should say. The basic body of observed data, the greatest body of observed data that is unexplained prior to my derivations is the Appendix A of your physics textbook. Planck's constant equals such and such. Speed of light equals such and such. Electron mass equals such and such. Elementary charge equals such and such. That page now is no longer to be labeled fundamental constants. They've all been derived from first principles. And every single definition of them, look at the math, look at the algebra, the numbers and the math are the judge, not the existing body of physicists who have failed to derive these. They're not the judge. The judge is the numbers and the math only.
Well, that would
And
be
the
an
speed.
example of being able to explain more things than some other theory. Although I see we do have a
Well,
new person
I
here.
would say so,
We have a new
but I'm
person
here to
here.
find something to destroy my theory.
We have a new person here, Toby. So
Hi,
can
Toby.
you talk? Can we hear you?
Yes, can you hear me?
You're very quiet, but we can barely hear you.
Okay, can you hear me now?
A little bit better. It's still a little bit quiet, but go ahead. Did you
Keep
have
on increasing your mic volume, Toby.
Yeah, let me up my mic volume here.
Yeah, I had a problem like that last week. It's some
And
complicated
welcome,
setting.
Toby.
Okay, here we go. Let's see. No, my input volume is on max here, so I'm going to have to get a microphone or hug the computer. But basically, I'm an electrical engineer, but more of a shade tree mechanic. You guys can handle the math. I worked for many years with a man named Tiwari, who, when he retired, was the executive director of the Nuclear Power Corporation of India. So am I coming through loud and clear?
Yeah, we can hear you.
Okay, so Tiwari published a book on his space vortex theory, which he published initially in 1977. And this is the book. But he was able to derive all the fundamental constants based on his space vortex theory and his model of the electron. And his model of the electron indicated it was 2 orders of magnitude larger than is given as what Franklin has just described as kind of an arbitrary size given in standard physics textbooks. So basically, his theory is the electron is an interface between the ether and nothing. So the electron is a bubble floating in the ether, rotating at the speed of light, which allows it to maintain its constant size. And then he goes on to derive the fundamental properties, constants of the physical universe, which we're all familiar with. So I was kind of interested in sharing this work with you two guys because you can handle the math. Those differential equations and calculus left me 50 years ago as soon as I graduated. And so I'll be interested in you guys emailing you a copy and seeing getting some feedback from you, what you think of his ideas.
So let's see. What was the name of his book?
That's Universal Principles of Space and Matter.
Universal. So is that something you can get on Amazon?
I don't think so. I just had the personal relationship with him since about 1982. He passed away 2 years ago. And I don't know if that book is in print or not. It's, long out of print. It may be available somewhere. But I have.
Well, let's see here. Well, apparently you can, let's see here. Universal Principles of Space and Matter. Well, that looks like I've got that by Parasamari Tiwari, because he's got his website, I guess.
Yeah, Paramahamsa Tiwari. Yeah, I ran that website for 17 years, and then I turned it over to his kids. I've got the PDF copy of it. I could shoot that to you, Franklin, and you could shoot it to today's speakers.
Okay, yeah, if someone's interested in that.
I would be
You got
interested.
the PDF of that, all right?
Yeah.
Otherwise, that's there's a URL to that the published book, I guess, if they're still doing that. Although me personally, upon hearing that, I always have pretty violent objections against the idea that the electron is actually something which can be decomposed. Actually, I guess my shtick is, and it's just me, that I like to think of the electron as being truly fundamental, and that it can't be broken down into anything. It's not a vortex of anything. It's not a soliton, and it's not any way a torus. I would, but like I said, that's just kind of me. I think that kind of structure is too complex. Although my problem would be is if you ask me what really is an electron, I'd have to kind of shrug my shoulders and say it's exactly what we observe it to be, which is this speck which is so small we can't measure it, but emits a negative electron charge and has its antimatter partner, the positron, which is just as mysterious, but emits a positive electric field around it. But fundamentally disagree with any conception that, say, the electron is made out of some ether in a vortex, which kind of sounds like what he's talking about there. I mean, is that what he's talking about? That
Yeah, he does say that the electron is the fundamental unit of mass or matter, or is a fundamental entity. It can't be broken down.
But what does he say? What's the relationship between that? Because you mentioned ether existing. So if the electron is the fundamental particle, then what is the ether?
Good question.
I mean, is there an answer there?
Yeah. He derives the properties of the ether.
Well, I mean, I think you still have to answer, what is the ether? I mean, if you're like me and you say that the only particle in the universe is, say, the positrons and the electrons, and even those are really the same things, except for the electric field that they emulate, then if you're an etherist, you either have to think that the ether is something different than that, and then it becomes the question of, well, then what's the fundamental particle of the ether, right? If it's not the electron or the positron. And then you have to make up something else, right?
If you're looking for particles. Why does it have to be particles?
Well, me personally, I think it has to be particles because we like to have a physical world and we know what particles are. We think they're those things that we can hold in our hand and such. My personal solution to that conundrum is to say that the ether is made out of positrons and electrons. It's in fact a positron-electron seat. And it's neutrally charged, so we can't see it. So actually the ether particle is more complex. It's made out of the fundamental particles, which I believe are the positrons and the electrons. So that's how I kind of get around that conundrum. I make the ether be a composite particle. And so we can still maintain the ether, the electron and the positron as the fundamental features of the universe, and still explain what the ether is in terms of the fundamental particles.
Yeah, I think the response here would be that the ether is non-material, so you can't have particles in non-material.
Yeah, but I think that's not a correct way to solve the problem, to say that the ether is non-particle.
It has no properties that the material world has, or the material. It's a material world is a subset of the ether.
So how do we compare those two? So I'll ask James. So James, try to be a dispassionate third-party observer here. And if you have to choose between theories of the ether, where either the ether is composed of particles, like I say, like it's composed of positrons and electrons, or you have to choose between the ether being non-material. And I'm not even sure what non-material would mean. how would you judge that?
In response, I would agree with more with Franklin's concept of ether composed of particles. You might recall last week I presented some of my information on vacuum composition, where if we cool down a system to absolute 0 Kelvin, which we can do in a simulation, can't do it in real life. We can almost get there, but in a simulation, we can get all the way there, where all the kinetic energy in the initial state, which is a random distribution of quanta in a volume at a certain density that one can select, so that all of those quanta, which might represent heat, in the form of electromagnetic radiation or kinetic energy in terms of particle motion, when all of that leaves the simulated volume and you get down to 0 Kelvin, there's no particle motion anymore, and you can then look at what the actual composition of an electron and a d quark and so in a positron, etc., are, without any clouding from kinetic energy being in the system. And you can see also, relative to the ether question, that 88% is my estimate in the most recent paper on www.binary-mechanics.com called Vacuum Composition, that 88% of the quanta at 0 Kelvin is not associated with the particles, but is the perfect vacuum. So the perfect vacuum is not thought in my work to be empty space at all. Now, so that agreeing with Franklin concerning the, he's out of the room. Agreeing with Franklin as far as the, if you want to think of that perfect vacuum as the ether, what I find in my work is that independent of the velocity of the object emitting light energy, EM radiation, in other words, the velocity of the EM radiation is constant, or is, well, not exactly constant, but is independent of the velocity of the object emitting the radiation. So that might contradict with at least some naive views about ether work that I have read about in the past, that people will say, well, the speed of light from a fast-moving object must be the sum of the speed of the object emitting the light plus the speed of light and blah, blah, blah. That's not true, and that's, by the way, in agreement with special relativity, that the speed of light is sort of a constant. What I add to that is that the speed of light also depends upon this density of quanta in what we call perfect vacuum. It's not, so that contradicts Einstein's idea that it's exactly constant. And because of that, since the LIGO work on detecting gravity waves, etc., it can be, I view that as experimental evidence in favor supporting my work, because if those waves are actually slight changes in quanta density in the vacuum, the speed of light would change slightly in one arm of the LIGO apparatus compared to the other arm of the Michelson interferometer apparatus, which is basically what they're doing, showing an incoherence in the laser beam that they use, and to detect gravitational waves, which would be, by definition, slight variations in vacuum quanta density being propagated, from wherever. So I don't know. So Franklin asked me to talk about the particle idea of ether. I guess what was the alternative, Franklin?
Well, that ether is non-material.
Non-material. Well, sorry, I'm only interested in physics. I mean, what's non-material? Spirits, ghosts, goblins?
I suppose non-material, maybe this might appeal to you, that, if the universe
I think there are forums on religious ideas,
Well, it could be. It could be ether is non-material, like you say. If in simulation theory, if the universe is in fact implemented on a computer, then the ether could simply be the defined geometric quanta of space as defined by the computer, in which case
I call that absolute vacuum.
it would be
Okay, first
non-material.
you say non-material, meaning a volume with no energy quanta. Well, that's okay with me. So I guess I would have to say both. But places where there are absolute vacuum is 0 state bits in a volume. Okay, and
Yeah, but I'm not saying that.
sizable place with absolute vacuum would quickly capture incoming quanta in the electron and proton bit cycles and would no longer be absolute value anymore.
Yeah, but that's not what I would be saying. I would be saying that there is actually no place in the universe which is the actual vacuum, except for maybe the spaces between positrons and electrons. But those so completely define the available space, meaning they fill up all the slots, that there is virtually no spot in the universe that's actually at 0. And that every spot you could look at has either a positron or an electron in it, is what I would think. But once again, these are the various theories. And, getting back to the original thing here, I'm just going to wrap it up here. Bill Lucas brought up Robert Destini's website and how we should all just consider the possibility of poly theories. And we should go and try and determine, say, amongst us, and we've discussed various possible different, say, atomic theories. We've discussed, say, Bill Lucas's theory. I have my own theory. We've discussed possibilities of what space is made out of, whether space is made out of, say, materials or not materials. Those are all examples of, different possible theories, which all, as Robert says, all actually agree with the existing data, or at least some existing data that we can find. And then as James goes, he made a whole list of, okay, once you do that, then what other things do you look at to determine whose theory is more truthful? Which one explains more, which ones predict more, which ones, perhaps the simplicity might fall into that. And then to not be, completely wedded to our own pet theories, which I think, many of us in the dissident community could correctly be accused of. So it's like, I think there was the book, Science on the Fringe by Wortham or something like that. Say they all have like the Jesus complex and that we're all here to save the world, and just as soon as everyone figures out that I'm right, then the world will be better, right? Okay, but with everyone thinking that way, that's not entirely useful. So because no one ever budges off of their existing theories or tries to find contradictory evidence or things like that. So, but it's very interesting that we brought that up, and food for thought. But I think we've come to the end of our science chat here, and thanks for everyone participating, and hopefully we'll see you here sometime next week. Okay, so ta-ta.